All
And
right.
Ron.
Thank you. Oh, yeah. Thank you so much for leading that session. And thank you, Greg Riley, who stepped out for introducing that. That was incredible and just so generating, which is so wonderful. As Sean said, we have one more session, and then we'll do some closing thoughts and wraps. So we're going to look into valorization of wastewater using microbial fuel cells, presented by Daniela Moreno and Aradhana Singh from the Water and Environmental Engineering Group, the WEEG or WEEG, at the University of Southampton in the UK. And you should have sharing power,
Hmm.
I believe. Are you with us?
Yes.
Oh, there
Thank
you
you.
are.
Yeah.
Great.
And so glad to have you join us. I think this is our first year having presentations from the UK, and we've been happy to be graced with several from from there. So excited to hear about your work. And I've also enjoyed seeing you throughout the summit. So thank you for sticking with us, Daniela.
Thank you. Can you now see my screen? Can you hear me? Is the volume okay?
We can hear you, but I'm not seeing your screen just yet.
Okay, let me try again. Um, Surely, it says I have two screens, so I'm trying to just get it on the one that there is. Okay, here we go again. Can you
Promising, yes.
see it now?
Yes, now we can.
Okay. Does it look okay? Can you see a full screen now? No presenter mode?
Yes, you're all good.
Looks great.
Okay. Well, thank you everyone for sticking until the end, specifically because we are the last presentation. So thank you in advance for your attention. I know it's been couple 3 days full of information, but anyway, it's been a really nice community. I felt really welcome on the activities we've done, so thank you very much for that. Today, my colleague and I, Aradhana, will be presenting you what we call microbial fuel cells and how do we use this technology to valorize wastewater. So I will just have a little outline of how the presentation will look like. I will introduce who are we, where are we. We are going to stretch a little bit the topic into the water and energy nexus and why is this important for our microbial fuel cells. At that point, we're going to get a bit technical, but you'll have to bear with me. And then we're going to go into the case studies and the impact that these studies have had and how this all led up to our pre-startup on microbial fuel cells. Well, my name is Daniela. You can call me Dani. My background is mainly on molecular biology and microbial electrochemistry, but now I'm focusing on developing these microbial fuel cells and seeing how we can use them as biosensors. My colleague Aradhana, on the other hand, she has a chemistry and industrial background and microbiology as well. She's currently helped us design and optimize the fuel cells and jumping into the fuel installations of this. Now, the man that you see at the very left, he is our supervisor, and we're kind of doing this presentation on his behalf. He is a very intelligent human being. His research income in the past 12 years has been more than £6 million, so quite a lot, and more than 100 peer-reviewed journal articles as well. So he's quite intelligent. I know he will be seeing this on repeat, so hello when you see this. Right. We come from the Water and Environmental Engineering Research Group at the University of Southampton, which has three main disciplines or pillars, and we like to explain it like this. We have dirty water people, which is essentially us. We work with wastewater treatment technologies and all this stuff. We have fish people, all the ecologists, and then we have clean water, which they do more simulations with big towing tanks and things like that. We don't really give that much detail every time we introduce ourselves, but I think in this case it was important to make the differentiation because although the Water and Environmental Engineering group does encompass different technologies within the sanitation, we have a specific team deeply linked with urine in this research with microbial fuel cells. And you will see what I mean with this in a couple more slides. Now, mentioning where we are, I think is equally important because we are one of the few research groups of the university based in the science park of the university. And more specifically, we are part of this hub called Future Towns Innovation Hub. We're basically on the same building. This hub has both physical and a virtual innovation hub, and it's almost like having a matchmaker next to you because they connect stakeholders with relevant expertise and see how this can drive innovation by using regional towns and probably using them as test beds. This helps a lot in sustainable urban development of these regional towns because otherwise they get forgotten. And at least on the south of England, innovation normally happens on the city, and they leave towns unable to catch up with this development. And a lot of the times that relevant expertise needed happens to be us researchers, but it can also be businesses around in the science park or even in our same building. So it's really nice to have them around, and this has also helped us to get grants and get super close with local policymakers and big companies on the water sector. So we're really lucky. Now, jumping into the energy and water nexus. Well, I know urine and sanitation have been the star of the summit, but I'm going to stretch the topic a bit into energy, and we'll go back to urine in just a second. I just wanted to share this powerful message that we have very much cemented in our way of thinking in our lab. And this has to do with the interdependency there is in between the energy and the water sector. Because for our current scenarios and how a lot of cities are currently designed, we have to make a real effort into rethinking our systems and not to increase the interdependency between these two sectors. And honestly, it has been really inspiring to see more and more solutions of the grid and how people are trying to reivindicate the designs and the concepts in our waste management. And I don't know if you share the sentiment, hopefully you do, but attending to this event has been really relieving and inspiring, seeing how the people redesign the concepts and then adapt it to circumstances and to their local people. And it's almost relieving. And I think, at least for me, it's really nice to see people working on this air with me that actually see the problem, and not only they see the problem, but they're working in solutions and being really proactive. So hopefully all of us meeting on the finish line will look like this girl's in the picture after our startups and our technologies and solutions and policies are implemented there in the real world. Okay, but going back to our water and energy problem, I find it really intriguing how nature has solutions to problems that even humans create for themselves. And it is always a good idea to just pause a minute and think, if I was nature, how would I solve this? How can I create that direct link between the wastewater and the energy naturally? And then you might start thinking, why is there a cow in the picture? But I will start with this example with ruminants because we know they're mostly herbivorous animals. We know they eat a lot of fiber in form of plants and it's on the regular diet. But funny enough, they cannot digest it. Ruminants lack the machinery from their digestion. So someone else is doing it for them. And the fermentation of these plants happen to be, due to symbiotic relationship they have with microorganisms inside their guts. These microorganisms are capable of producing enzymes to degrade these plant polymers, and they give the animal the energy they need while digesting it, or in other words, transforming the waste. Now, thinking along the same lines, is there something us humans can use to transform our waste into energy directly? And I am hoping that you are thinking, surely yes. Now, this is where I'm going to start getting a bit more technical, so just bear with me. We have some bacteria that can actually do this for us, and they are called electroactive bacteria. Now, in these reactions, you see to the left At the very left, you see different carbon sources that could be transformed by these bacteria. And in this transformation, we end up with different number of electrons, as we see all the way to the right. And these electrons is what we're really interested in. In simpler words to explain this, the carbon source acts as an electron donor, but the bacteria then need an electron acceptor, which in other cases, this tends to be another chemical compound. However, these bacteria have the peculiarity of having preferences for metals. Now, keep this in mind. They have a preference to give the electron to metals. There we are, a little metal. Now, if we say provide a continuous source of carbon to this bacteria and say I choose domestic water, the bacteria will need this to grow and reproduce, and this means I will have a continuous supply of electrons. And then if I provide this bacteria with a grounded metal wire, the electrons should be continuously flowing through this wire. Now, I insist on the continuous and continuity because the continuous flow of electrons is what we use currently to create conventional current. Now you can connect a light bulb to your wire and congratulations, you see electricity. Now this is how it actually looks. You can use conductive materials with good porosity and conductivity in high surface area to grow this type of bacteria. And in this specific example, we're using carbon veil. So this is a single fiber covered by the bacteria in the carbon veil. Now imagine we don't need to burn fossil fuels. There's no need to connect to the grid because while you're treating wastewater, you're producing your own electricity and donating those electrons to a wire. Now someone really smart thought about this and putting this design into what resembles a galvanic cell. This allowed the introduction of a membrane that is able to separate the anode, which will be our electron donor side, from the cathode, which will be our electron acceptor side. Realistically speaking, you can do it in any shape you want as long as you have these two chambers. Now, there was a problem. How can then we get more power? At first, you logically think, well, if I want more electrical power, I make a bigger reactor, right? That holds more wastewater equals more bacteria that generate more power, right? But this is not chemical reactors. We're talking about teeny tiny living things, which are greatly affected by the distance there is to the electron acceptor. So essentially, the electron has to travel to be received by a conductive material. And some bacteria need direct contact with the conductive materials, others need a little arm-like structure extending to reach the conductive material, like the one you see here. And some others have the capacity to create for themselves short distance shuttles to transport the electron to the nearest conductive material. But regardless of the method of electron transport, the distance in between limits how big can we make this most of the times. This limitation, if you want to call it like that, explain a lot why researchers at that time were observing higher powers with smaller reactors. And eventually, a lot of them gave in into this trend of miniaturization, and this led into modular designs and even changes of shape on the design into circular reactors, which help expand the surface area of the exposed bacteria. Now, on a way, this was beneficial for innovation because now imagine this works like Legos. You have two massive block of Legos and there's not really much you can do with them. But if you break them down and you have instead 15 or 50 small pieces, you will be able to shape them better into design. Now, initially, this led to MFCs powering a lot of robotics and powering sensors. Then the cell became the sensor itself because you will analyze the data coming out of the cell, and this will be a direct link of indicating organic load. The more organic load, the more microbial activity, and then an increase of power. I can show you briefly, very briefly, the real size of the model. In the meantime, Our supervisor moved on then after doing this into exploring the feasibility using urine. And this led into amazing study cases. Sorry, it looks a bit blurry, but at least you can see the size. It's not something small, but there's a lot of small units. Anyway, I would like to transition now into urine, to leave the floor to my colleague Aradhana, and she will guide you through this field trials and study cases with real urine and how we were then led into our pre-startup. So Aradhana, if you want to.
Am I audible?
Yes, we can hear you.
Okay. Okay.
Great.
So please bear with me. I'll share my screen first.
Perfect.
Okay. My screen is visible to everyone, I guess.
Yes, we can
So
see
I
that.
can,
Thank you.
okay. Okay. So I think I can continue. Hi, everyone. My name is Aradhana Singh. I'm a postdoctoral researcher in the group. And I joined the group in 2023 as an experimentalist on the Gates Foundation project called, sorry, should I do with this? Should I? Okay. Yeah. Yeah, I joined the group in 2023 as an experimentalist on the Gates Foundation project called Urine 3City, which is an extension of the previous project of Yanis called P-Power. So I have a background in the environmental chemistry and microbiology, as Danny has already mentioned. So in this project, which is called Urine 3City, I'm helping on material testing and design optimization for field installations of microbial fuel cell. So today my job is to take you through amazing work that has been done within the project and also what we are doing currently and some of our efforts towards commercialization of our technology. Okay. Now, what you see here is one of the first field installations of our technology, which was happened in previous University of Yanis, which was University of Bristol in one of the campus in the university in 2015. So they used around 8 MFC modules of microbial. I'm so sorry. What happened? Okay. So they used 8 modules of microbial fuel cell consisting of many individual microbial fuel cells. And they were able to produce around 0.4 watt of electricity spanning around 75 hours, I guess, if I'm not wrong. Yeah. So that was one of the first trials of this P-Power project. And COD chemical oxygen demand, which was also reduced to around 90% observed in the campus setting. So yeah, this was one of the first proof of the concept in the field trial with modest usage, I can say 5 to 10 users per day with hydraulic retention time very long, which is around 2 to 3 weeks. And with low capacity, I would say around 2.5 to 5 liters. And that's why we were able to produce good electricity with good retention time of 2 to 3. Oh, I've already mentioned that. I'll go to the next slide. Sorry, I don't know what's happening. Okay. After that came on the second installation, which was done in the same year. Those people who know about UK, they know about Glastonbury Festival, which is a big festival in the UK. So they installed the technology in the in the festival, and a lot of people used our facility, and I think they used the same module which they have used in the university. Along with that, they used 4 more modules. There were a total of 12 MFC modules installed in the festival, and they were fortunate enough to produce around 19.2 watt of electricity for 24 hours. And this proves that our MFC-based technology is a sustainable solution to sanitation, that also provides electricity at individual and as well as on community levels, because so many people use our facility in the festival. So after the successful field installation in 2015, they continued the installation in 2016, 2017, and as well as in 2019. If I go, yeah. So 4 successful years of field installation in the festival. And they also conducted a survey where around 92% of the users said that they were really happy to use the facility, and they believe in the ambition of this P-power technology, so which was quite motivating for all of us as a researcher. Okay. Now, one of the significant work of P-power technology was tested in Uganda in one of the secondary schools near Kisoro town in Uganda. So the purpose was to install a P-power system to supply lighting for a toilet block, which had no electrical lighting before. This is surprising. This is shocking for us to accept this fact that there are many places in the world which still has no lightning, right? But yes, there are so many places, and we as a researcher on microbial fuel cell had the ambition to light all of the places, not all of the places, but as many places as possible with our technology. So, and here in Uganda, in the school, our system was working for around 20 months, near to 2 years. And this was a girls' school, and it was used to light their toilet in the night. So these girls, we were not using the facility in the night, but after our MFC technology installation, they were able to use the toilet in the night. So it was a successful demonstration and installation of our technology, I would say. Again, we conducted a social survey, and 97% of the respondents said that they really like the P-power technology. And before installation, as I mentioned, 76% of the students said that they did not feel safe using the latrines at night. But after the system, 86% said that the lightning made them feel safer after the installation. So similar to Uganda installation, P-power was also installed in Nairobi, Kenya, with a similar level of community engagement and performance output. This is one other example of our technology. So Professor Yanis collaborated with European collaborators with a funding of 3.2 million euro. This project was called as Living Architecture. I'll just show you here. So the purpose here was to build, living buildings using microbial fuel cells. And these microbial fuel cells used as a sensor, can be integrated in the wall, which will produce electricity, sense temperature, humidity, and this is, I would say, an ambitious project still going on. We have a lot of ambitions to achieve in this project. And so, yeah, I will not go much in detail of this project. I will quickly go to, so this is an active project that we are still doing in our lab in University of Southampton. This is called MyHigh, which is an integration of microbial fuel cell with hydroponics. So the MyHigh project is part of Horizon funding, and it explores how microbial fuel cells can support the plant growth. So what happens, the catholites, which are synthesized as a byproduct in a microbial fuel cell, which I will explain you later how we synthesize catholites in microbial fuel cells. So these catholites are rich in nutrients, and these nutrients can act as a fertilizer for the growth of microbial fuel cells. So that is a project that is still going on in our lab, and I can show you how we produce these catholites, which can be used as a fertilizer. This you see here is an example of microbial fuel cell. We use urine as a source of feedstock in our microbial fuel cell in the anode chamber here. And then after electrons and protons are being produced, as Danny has mentioned already, how it is being produced due to the activity of microorganisms on these urine. And these electrons and protons are then transferred to the cathode chamber, This cathode is open to the air, oxygen comes in, and there's a reaction happens that's called oxygen reduction reaction. And due to this reduction reaction, there's a liquid being produced. That liquid is nothing else but water, clear water, H2O. But then due to electroosmotic drag, the nutrients from the urine, the rich, good nutrients from urine are also transferred to the cathode. So this liquid, H2O, is mixed with highly rich nutrients of urine, and which is also clean, toxic free, free from microorganisms. So you see the double benefits here, electricity production as well as clean liquid production, which is rich in nutrients, and then that nutrients are being used in the growth of plants or crops or whatever you want. So that is what is the ambition of my high project, to develop efficient ways of generating good quality catholites by working on designing, hydraulics, materials, and many other things of microbial fuel cell. Okay, I'll take you our efforts towards commercialization. So it's called Microbial Electrochemical Technology Commercialization, METC, which is a cost action that brings together researchers, industry, and stakeholders to accelerate the commercial uptake of our technology. This METC focuses on building the gap between laboratory MET advances and market-ready applications. Cost action highlights support for scaling up, standardization, and business model development for MET systems. Its goal is to enable METs to become viable, deployable solutions for wastewater treatment, resource recovery, and sustainable energy. And I would like to bring your focus also on Cost Innovator Grant. Those who don't know about Cost Innovator Grant, COST stands for European Cooperation in Science and Technology. They give grants to research and fund their research. So this CIG grant, Cost Innovator Grant, is basically given to one among 5 competitive, already efficient cost programs, and we were fortunate enough to get one. So you can see, you can understand the potential of our technology for commercialization. Okay, to go. I don't know how. Next slide. All right. Okay. This is our group of researchers. Professor Yanis Aropoulos, Danny has already explained about him. He is a world-renowned expert on MFC technology, who first bring the idea of using urine in microbial fuel cell. Background-wise, he's an electronic engineer, but now we cannot put him in one expertise because he's working for so long on microbial fuel cell. And one of the beauty of working on microbial fuel cell is that you have to be expert on microbiology, chemistry, electronics, and whatnot, actually. And you already know about myself and Danny. Other than that, we have 3 more PhD students, Ye, Jack, and Natasha. Ye and Jack are chemical engineers. They are working on, Ye is working on designing and producing new materials using novel techniques of 3D printing. Jack is trying to integrate the concept of forward osmosis in the microbial fuel cell. Divyajyoti is the lead researcher on the MyHigh project, who is developing new ways of generating good quality catholites from microbial fuel cell. Natasha is also helping on the MyHigh project. And Jeremy is one of the technical assistants that help us in our day-to-day lab activities as well as in field installations. These are few of our collaborators and sponsors who have helped us in achieving our goals and continue to help us in, I would say, developing a technology of the future. Thank you so much, everyone. I would say our ambition is to develop a technology which is purely sustainable, renewable, organic, and to lit all of the places around the world, not all, most of the places around the world, by help of these sponsors. And thank you so much, everyone, for listening. And we are ready to take your questions. Thank you.
Thank you so much. Yeah, just seeing the power of what it can do for safety, and there's just so much power in this beyond, I think, beyond first sight. You know, there's just like there's so many intersections from, and so thank you for bringing another one of those into the conversation. We'll give a moment if there are questions in the chat. I know people have been showing up all day and having great questions and being so engaged. We so appreciate it. There is one question in the chat. How does the microbial fuel cell manage any membrane fouling when operating with urine and with sewage? I have a feeling Abe Noe Hayes wrote that.
Yeah.
There's,
So,
I,
okay, Danny,
Ma-
if you would
do you
like to
want to
answer.
take it?
Go on.
I would say one, maybe you can say the other, but I know one
Okay.
of our how do we manage fouling and how do we manage clogging and all these problems that come with is using an adequate flow rate and hydraulics. So part of our design helps avoiding this and avoiding, for example, precipitation and things that do not help the membrane in functioning. I don't know if you want to complement this.
Yeah, we use very organic material like ceramics, and we have shown that if we in field installation, these ceramics were well efficient in working for more than 2 years. So yeah, I mean, if it can work without any maintenance for 2 years, I would say it's not bad in terms of material performance.
Great, thank you. We'll take the two other questions in the chat before we wrap up. Matthew Lippincott asks, can you share the energy potential in watts per liter? I think that's watts. Watt
Yeah.
hours per liter?
Yeah. What's the question? Sorry.
Can you share the energy potential in watt hours per liter?
Watt hours per liter. I think I have shown in one of the field installations, they have produced around 19 watt that was spanned for 24 hours. So if I have to say in hours, it can go hours and hours. And in liters, the potential we achieve from one teeny tiny microbial fuel cell of, I would say, 10 milliliter capacity, around 1.5 milliwatt, 1.5, yeah, 1.5 milliwatt per meter cube, per meter square. Yeah. I guess it's more or less same, around 1.5 to 2 milliwatt per liter.
Okay, thank you.
Yeah.
And a curiosity from Wamala, how did the P-Power project in Uganda progress?
It spanned for 2 years, around 20 months. They started in 2017 and it spanned up to 2019. And yeah, ambition was to still continue it, but I guess it was COVID or sometime around COVID that they have to stop it. But the good news is we are doing it again. We are going this year in Nairobi, not in Uganda, but we are installing our technology in Nairobi in this year in 2025, and we are hoping that we can continue to expand it for longer period of time.
Yeah,
Amazing.
ideally in these projects, it's not precisely that we go and maintain these systems. Like obviously we provide with the technical expertise and help,
Yeah,
but also to train
then
people for them to do the maintenance themselves, so we don't have to keep going and just handing the technology to the
yeah.
users.
Great. Thank you so much. And thank you for that research and for bringing it to the summit this year. Appreciate it.